As was mentioned, this is a story about a DNA sequencing technology, and it begins with this enzyme. It's obviously familiar to everybody here, and it's the main enzyme that's used in most sequencing technologies already. But I want to invite you to take a second look at it. This is the DNA polymerase enzyme, ubiquitous in nature. No life form exists and replicates DNA without it. And we think of it at Pacific Biosciences as a sequencing machine in and of itself, a nanorobot, if you will, that every time a cell replicates, searches across the genome, visits every base in sequence, and identifies those bases, records the information in the complementary strand, and as such, it is a sequencing machine. Now, it has a problem for us, technologically, which is that we don't know how to read its that is, after all, the complementary strand, every bit as difficult for us to read as the original. But if we forgive it for just a moment, that one shortcoming, look at its performance here. It's really quite extraordinary. In vivo, it can go 1,000 bases per second. The read line replication is not 800 bases, it's 800,000 bases in some of the complex eukaryotic replication forks. It uses essentially no reagents, less than a picogram of material used in effectively sequencing the entire genome, and it essentially never makes mistakes. So our challenge then is how to overcome this problem that we don't know how to read that complementary strand. The approach that Pacific Biosciences uses is to attach fluorescent labels to each of those 4 categories of nucleotides and then watch in real time as synthesis is undertaken. Every time a nucleotide is trapped in the polymerase, there's an opportunity to interrogate that fluorophore, thereby identifying, effectively you're eavesdropping or spying on the enzyme while it's undergoing template-directed synthesis. And in that way, we can identify the sequence. So you get pulses of fluorescent light from the sequence of colors. You would be able to then infer what the template sequence is. We call this single molecule real-time DNA sequencing. I think everybody's familiar with single molecule sequencing. I hope that by the end of this presentation to convince you that the combination of single molecules in real time is the only way to extract the full benefit of single molecule sequencing. The first problem that has to be overcome in order to envision watching a DNA polymerase in real time is to overcome a background fluorescence problem. This has to be a single molecule technology. If we're going to treat the polymerase as a sequencing machine, we have to look at one at a time. And that if we're looking at just one molecule, this is a single molecule detection platform. Single molecule detection has been around since the 1980s, but the concentrations of fluorescent analytes that can be tolerated in those systems before Pacific Biosciences was limited to a few nanomoles. And these DNA polymerases are much greedier. In order to remain fast, accurate, and processive, they require many times micromolars of nucleotides in order to be happy. This is where we part company from the other polymerase-based sequencing technologies in that other technologies, even these single molecule versions, have essentially punted on the real-time capacity of the enzyme. And instead, to deal with this background problem, they halt the activity of the polymerase, wash away the background-producing fluorophores, and then scan the system after that. That simplifies the technology, but it does so at the expense of both the read length and the cycle time. The cycle time, I think, is obvious because there are extensive washing steps that have to take place, but also the read length, because once you stop the DNA polymerase, it's never 100% clear that you can restart it. And that only systems that have been improved through billions of years of evolution are capable of getting to that 99.99 plus forward reaction efficiency that would lead to the possibility of very long read length. Well, at Pacific Biosciences from the beginning, we intended to make this a real-time technology. So instead of changing the action of polymerase, we decided we'd build a microscope that was 1,000 times better. We did that by borrowing a concept from classical electrodynamics known as waveguide transmission below cutoff. This is a concept that's very familiar to all of us. It's at work in the door of an ordinary microwave oven. That if you look carefully at your microwave oven door, there's a metal screen perforated with holes about 2 millimeters in diameter. They're there, of course, to let you see your food, but the real function of the screen is to prevent the microwaves from coming out and cooking you while you're peering in. The reason it works is because the microwaves are about 12 centimeters in wavelength, and the hole is about 2 millimeters in diameter. And because of classical electrodynamics, a wavelength, a photon with a wavelength that large simply can't go through such a small hole. It bounces off as if the hole simply wasn't there. Well, the same thing happens at the nanoscale. We use now not microwaves, but visible light photons with a wavelength of 500 to 700 nanometers. And we use a hole that is now a few tens of nanometers in diameter. The same thing happens. A photon that is transmitted up through a transparent glass substrate and attempts to penetrate through a cylindrical hole in this metallic film is exponentially attenuated over the length of that cylindrical tube. And the result is, while there is an illuminated zone in the bottom of the hole, that all of the fluorescent nucleotides that are very close by, just 100 nanometers away, are kept in the dark. And therefore, they do not contribute to the background noise. The volume that we get is more than 3 orders of magnitude smaller than the confocal diffraction limited microscopy. It has a volume of about 20 zeptoliters, or 20 times 10 times 21 liters. It's the first time that an observation system existed that would allow single molecule interrogation of polymerases at the relevant concentrations. The second issue that has to be overcome is the question of how to attach a fluorescent label to a nucleotide without disrupting function. The traditional way of doing this was through base linking, attaching fluorophore to the nucleobase. So the fluorophore becomes a permanent part of the DNA double helix, and that works fine. They're tolerated by polymerases at a low substitution rate, 1 in 100, 1 in 10 are easily tolerated. But at 100% substitution rate, they simply don't work. The reason is because these fluorescent side groups are big and bulky. They interfere with each other geometrically, and they prevent the thing from being recognized by the polymerases of DNA double helix. Of course, another problem, even if you could get 100% substitution, the continued presence of those fluorophores would just allow a buildup of fluorescent light. So the second generation DNA sequencing technologies that are based on DNA polymerase and base linking use some form or another of method to remove those side chains, either chemical or photochemical, and they do so again at the cost of cycle time and relength. At PacBio, we developed a new method for labeling nucleotides, and instead of attaching to the nucleobase, we attach to the terminal phosphate moiety. By doing that, an important thing happens. The enzyme, the natural course of catalysis, cuts that alpha-beta phosphate linkage, and in a natural system, those last two phosphates diffuse away as a metabolic waste product of polymerization. And by attaching our fluorophore to that leaving group, it's there during catalysis, but once catalysis is complete, it's flipped away from that reaction with 100% because after all, this phosphate molecule here is required for that sugar phosphate backbone. The result is that the DNA that's being synthesized is absolutely natural, with no abnormalities. That's unique. There is no other labeling system that allows for natural DNA products, which is extremely important for sequencing accuracy. So when we put it all together, it looks like this. You have the polymerase, the template that we wish to sequence in the bottom of one of our detection structures, which we call a zero-mode waveguide because of its electrodynamic characteristics. And diffusion is the force that brings the nucleotides to the reaction. It's extremely fast on these size scales, just 100 milliseconds, 10 milliseconds is what's required to diffuse in and out of the structure. So there are thousands of sampling events per second between these nucleotides and the DNA polymerase active site. But despite that, because that detection volume is so small, it's empty most of the time. And that leads to this very low and constant fluorescent background signal when there's not a catalysis event underway. When there is a cognate binding event, so that there's a correctly matched nucleotide, the fluorophore and the nucleotide are trapped for a comparatively much longer period of time, tens to hundreds of milliseconds, about 4 orders of magnitude longer. So long that if I kept on at this scale, we'd be here all afternoon, so I need to fast forward to the end when that catalysis takes place. The enzyme breaks that bond, the fluorophore is flipped away, and it diffuses. Fluorescence returns back down to baseline. The enzyme will translocate to the next position spontaneously, and the whole process can repeat. There's binding, there's detection, translocation, binding again, and this process repeats ad infinitum. After the event is complete, it returns the system back to precisely the same state that it was in before the binding event, which you'll see later is very important. In real time, it looks like this, where there are several bases incorporated per second by that one polymerase. And this is the way that we implemented single molecule real-time DNA. I want to show you just a little bit about the instrument that we use for the analysis, because it will help with understanding the data that I'll show you later. It is conceptually like a fluorescence microscope, but in order to conserve on photons and also cameras to go into the system, we use a prism element, which is inserted here in the optical path, and has the effect of taking the light from each thermal waveguide that would otherwise all arrive at a single point on the camera, and it smears it out into a rainbow, so that each thermal waveguide has its own section of real estate in which its emission spectrum is being analyzed. So with one camera, we can both detect pulses and analyze the color distribution. To put you in the position of the camera, it looks like this. I'm going to show you a movie in a moment that has three phases. The first one is just a simple transillumination, where we're using a very sensitive camera to get that tiny amount of light that leaks through, just to illustrate where the thermal waveguides are. Followed by the beginning of the experiment, where at the start we have not all four of the nucleotides there. There is one nucleotide there that is undergoing cognate sampling in the active site, because there's all of the polymerase advanced to the point where they require the same nucleotide. And then we start the reaction where we add the remaining nucleotides that are needed, and sequencing begins. So let me show you that movie. So here we are looking at just the transillumination, showing the positions. This is a cognate sampling, so all of these are the same color. And then in just a moment, right? My movie stopped. There. Actually, I'm going to show that again. You missed a good bit. So now we're looking at sequencing for 3,000 holes simultaneously operating, in this case, between 3 and 5 bases per second. Let me just show you that movie again. So here's the positions of thermal waveguides, followed by cognate sampling, and then there's a hot start where we inject in the remaining nucleotides and it commences. And what you're seeing, the reason it looks different is because now you're seeing those different color channels in the rows in between where you originally saw the thermal waveguides. So this is, right here, about 36 megabases per hour of information streaming out at you. Now, not all of that is useful, because this array is slightly overloaded, which means that many of those holes have more than one polymerase in it. But there's a Poisson limitation that says that we can reach about a third of those without any additional measures to have useful data coming out. And that shortly after our shipment, which I'll talk about later, we will get to the point where every single one of those holes is producing useful sequence information. I'm going to show you a trace from running very much like the one that you saw there. I'm going to just get it started because it's going to take a while. So this is what the information coming out looks like, where there are elevations in the fluorescence, and because we have the spectral information to identify which fluorescence channel is responsible for that elevation. The sequence is spread out like a conventional electropyramid. There's an elevation on the C channel, we call it C, etc. And there's one pulse for each base incorporated. So in homopolymer regions, there's a separate pulse for each base incorporated. Now I need to get on with my talk because this is going to go on for some time, so I'm going to park that down here at the bottom, and we'll continue like that for the rest of the time of talk. And I'll talk more about that. This is going approximately real time, which is another feature that I hope that you'll appreciate by the end of the talk. It's a very different thing, sequencing in real time, from the culture and the granularity and texture of the workflow. I want to talk about the sample prep that we use to extract this sequence. We start with genomic DNA. You can fragment it by the method of your choice. I'll focus in on just one strand, but of course the steps that I'm going to show you are being done in parallel on all of the DNA strands. We use hairpin adapters that have self-complementary portion that are ligated onto the ends. The result is you get a molecule that, while it's still structurally linear, this is still that original piece of genomic DNA originating from the origins of the sequence, but it's now topologically circular, which I'll show you in a moment has important consequences. Of course, it looks like a dumbbell, but since we're doing smart sequencing, we can't call it a dumbbell, so it's a smart dumbbell. We prime into the single-stranded portion of that hairpin, and then after the polymerase is added, it's immobilized into the DNA guide. It sequences through that insert, it swings around the backside, and then spontaneously begins sequencing the antisense strand without any intervention. And then because our polymerase has strand displacing ability, with whatever read length the system has, it displaces the DNA that it has already synthesized. It just goes around that circle over and over and over again, increasing the accuracy on that one molecule. The workflow is very streamlined. It uses procedures that everybody here is familiar with that are all highly automatable. And instead of taking days, it takes hours. We applied this last November to the sequencing of Fusion back. At that time, in our production sequencing, we had an average read length of about 500 bases with a max around 2,000. I'll explain later why that's possible. We aligned it to the NCBI reference, and then because this was a manageable size back, just 107 kb, we sequenced the whole thing using samples that we could compare and see both false positives and false negatives. We found that we, at that time, could achieve about 240. We found 21 SNPs that were validated. We had a false negative rate, mid-3, which is something that we've been hard at work on since then. In the repetitive regions, for I think obvious reasons, performance was somewhat less good, but still found 13 real SNPs and mids of 7. Since then, we've improved the system tremendously, enough so that it made sense to take on the next logical step, which is to sequence E. coli, which we did in January. We used the K12MG1655 strain. We sequenced it to 38-fold coverage, aligned to the reference. We got 93% unambiguously covered. Our average read length by then improved to 600 bases with a max of about 3,000. Those parts of the genome that were covered 20x or greater came out to Q61, which means there were just 5 discrepancies. 4 of those were bona fide errors, but one of them was Sanger validated as a true positive variant. Over the entire genome, and that includes the highly duplicated regions, we were operating, and this was irrespective of fold coverage, we were at Q54. The physical coverage map looks like this. It's quite uniform. In order to analyze this, we can take a histogram of those data. That looks like this. The yellow bars are the actual coverage. The red dashed line is the ideal Poisson distribution. But taking a closer look at that coverage map, we notice that there is an undulation. And it turns out to be a well-known artifact that's stopping the E. coli culture in log phase growth. There's more DNA near the origin of replication. And if you subtract out that linear trend, it looks like this. And now the histogram is quite a bit better. We're unfamiliar with any sample prep and sequencing combination that can produce a distribution that is this close to unbiased. What small bias there is comes from a very slight GC coverage bias. This is from around 5% up to 90%. You can see there's no serious trending here. It remains a very good Poisson distribution of that entire range. And also the accuracy within a read is uniform. This makes sense. In the animation I showed you before, I said I'd get back to that. Because the system, after the cleavage of each nucleotide, is returned to exactly the same condition that it was in before, there's no reason to believe that the accuracy of the first base incorporated would be any different from the accuracy of the last base incorporated. We're very gratified to see in our E. coli data that that's true. This is a 1,200 base window, and that the accuracy varies by less than 5% coefficient of variation from the beginning to the end of each of those individual traces. We showed a plot like this in the science paper we published in January, and since then things have improved quite a lot. So much so that this plot is really no longer informative. We have to show the log of those data. This is now the familiar consensus QV. You can see that the approach towards consensus is very nearly free of systematic error, which is as we expected. There is, in single molecule sequencing, a higher rate of raw error due to the failures of single molecule detection, like flow bleaching, thermodynamics, etc. But there is a very low rate of systematic error for lots of interesting reasons that I don't have time to go in here. You can see right around 12-fold coverage, there's the emergence of a very slight mean. That is a small amount of systematic error. Such that by the time you get to 26x, there's probably about 10 QV points of systematic error. But that's a very low level for a sequencing system at this stage of development. And it's on track to crossing over Q60 by the time you get 26-fold. Of course, with the 4.6 negative genome, we ran out of room to improve definitively. That's really Q61. That'll be on its way soon. I'm going to zoom in on this 8-fold coverage data point here, where we have 8 molecules. These are 8 different molecules without the benefit of circular consensus sequencing, as I alluded to in an earlier slide. So this is just 8 molecules with 1 pass each contributing to the data, and a breakdown of the errors. And you'll see that there are significant differences between the different bases and the different error types. And this, it turns out, is not due to the underlying biochemistry of polymerization of those nucleotides, which is very fortunate. It is instead due to the fluor force that we can assign to them. And I'll show you that here. This is raw, unnormalized data coming off the system. And I'm going to mask out channels 3 and 4 so we can just see channels 1 and 2. And as you'll see, it's very clear that they are producing different levels of fluorescence output and therefore different error rates from those two channels. And it's obvious why. If you look at the fluorescence spectra, the emission spectra, the laser excitation is about here, and this is that first channel and the second channel, and they're about a factor of 2 because of the brightness. We have compounds in our development pipeline for that second channel that are as bright or brighter looking at the area under that spectrum than the channel 1 dynamical, and we're very excited about the performance we're getting from those in our development sequencing, which I'll talk a little bit more about later. I'm going to come back and touch on what this is. This, it turns out, is a 3,200 base read that was selected from our E. coli runs because it spans a 2.6 kilobase exact duplication in the E. coli genome. And it has unique non-repeating sequence on either side, allowing a completely unambiguous placement in the genome. We feel comfortable saying that this is the first time that a repeat of this size has ever been straddled by a single read. So the read length distribution that makes that possible, this I mentioned before that we had an average of 600 reads as long as 3,000, comes from the fact that the underlying read length distribution is an exponential. All of the processes that end reads in molecular sequencing tend to be single-step dependent processes that produce exponential distributions. And that you can see here, this fits very closely to a single exponent. Slight deviations there and there, but you can see very dominantly a single exponential distribution. And the decay constant, that corresponds to the average read length in our development sequencing system is just shy of 1,000 bases. So we, in January, well, in November, we exceeded 454 sequencing performance. In January, we exceeded Sander's sequencing read length. And we are now in excess of any sequencing technology in terms of read length. This exponential read length distribution gives us a flexibility built into the system so that I can run short reads and have high throughput. So for example, a formula-based read that at the end of which I still have the majority of those thermal radioids, the polymerases, are still producing sequence. Or I can do a long run, maybe even a multiple of the average read length. And by caching in throughput, because now only a fraction of the original polymerases are still contributing data. But nonetheless, even out to a multiple of the average read length, you can still get a usable quantity of reads. And that's how we extracted this 3.2 kilobase read with an average read length of just 1,000 bases. One of the things you can do other than scaffolding, as was alluded to earlier, with that extra read length, is that you can sequence around and around the same molecule and increase confidence in what that one molecule sequence is. This is that same read length distribution now converted from length into fold coverage on a short molecule. And I'll put that on those same data on a log scale so that I can point out that in some instances we got as many as 19-fold coverage on just one molecule. And the approach towards consensus within a molecule is actually better than between molecules. But the important thing about this is that by the time you've reached consensus, that this information is completely free of ambiguity that would be caused by heterogeneity in the sample. So be it polyploidy or heterogeneity or a pooled sample, then in this instance, you know that the consensus is looking at just one base. We've used that to examine our ability to find variance within the pool. We built two SMART-Bell DNA constructs that were the same, except for just one base, mixed them together in different ratios, and applied them to our sequencer. And we were very gratified to see, as we expected, because of the low bias we saw in the E. coli coverage, that there is also very little bias here, that if you put in 50-50, you get about 50% of those dual alleles back. If you put in 80-20, similarly, you get 80-20 back. And I'll zoom in on this lower end here, at where we're approaching down here to 0. These data suggest that even with today's system, which is a far cry from the system that we'll be shipping later next year, that we can detect a 1% minor variant inside the pool, which is close to, I think, the best that you can do with any other technology. So just a quick summary, our sequencing performance is ahead of plan. It's high speed, technology underlying sequencing chemistry is 30,000 times faster than second-generation systems that we can buy today. The sample preparation is greatly simplified. Sequencing reactions take minutes. This run was 25 minutes from beginning to end. If you attempted this, if it were even possible to reach these read lengths on second-generation systems, this same run at an hour per base would take over 4.5 months. The read length is much longer and has the capacity to be increased further still. We think that in 5 years' time, it could be at 20 to 50,000 bases in read length. It has the ability, flexibility that I talked about, plus the capability of doing molecular redundant sequencing. We right now have 12 prototypes in operation at our facility that are being applied to a combination of production sequencing as well as transport. We're on track for commercial delivery of this a version of this tool in the second half of 2010 that will make the throughput of these seem insignificant. I want to summarize by saying the aspect of this technology that I think excites us the most is where it's going in the future. If we imagine a point in the future where we could examine simultaneously 1 million thermal waveguides, and by then it will grant us that we can get from the 10 bases per second record that we've shown as of today and improve that fivefold to 50 bases per second. And to do that, we would need a camera that right now is not available. This would be a multi-megapixel camera, either CCD or CMOS, that comes with on-chip amplification that gives a single photon sensitivity. But if we combine all of these technologies together, the outcome is somewhat surprising. It's over 100 gigabases per hour. If we do this calculation exactly, it turns out to be 180 gigabases per hour throughput. That's enough to do on one chip an entire human genome in less than 15 minutes. And the cost of that chip doesn't change between now and then, nor does the cost of the reagents applied to the system change. Because it's in the molecular sequencing, we're consuming essentially no reagents during the process of that run. So by 2013, we feel very confident that our technology will exceed this 1 million thermal waveguide limit, perhaps even by a margin. There's no fundamental reason why real-time sequencing can't approach the same multiplex levels that second-generation systems have. And at that point, it will really transform sequencing. In the early days of TacBio, some of the VCs complained that they thought we were trying to distribute a 1 million gallon per hour bathtub faucet that nobody would need. Well, it turns out that if we're going to be serious about using sequencing in human diagnostics, this is exactly the throughput level that you need. This instrument, if you put it on the floor at LabCorp, would be just about the slowest diagnostic test that they have. This is a 15 minutes per sample is a relatively slow human diagnostic test. With that, I want to thank the team that really did all the work. And it's my privilege to be able to stand up here and take all the credit. The reality is that the team back in bioscience did all the work, and I spent all my time standing up and giving talks like this. And also, I want to thank the NHGRI that gave us grant funding at a crucial time as well, without which this environment would never come to existence. And also to thank our university collaborators, Walnut from Craig that originated this technology at Cornell, and then the nanofabrication facilities at Cornell and Stanford, without which we couldn't have done this. With that, thank you. Absolutely, I'd love to. Those are paused.
What's the question?
The question was about in that trace, there's running on the bottom, there are gaps. This comes from pausing in DNA polymerase. This is a phenomenon that takes place with all polymerases under all circumstances. And it happens in second generation and in Sanger sequencing as well. In those systems, it causes systematic error. It can degrade read length, it can cause carry forward or hold back, and either decreases read length or causes systematic error. Single molecule real-time DNA sequencing is immune to those errors because, as you can see, what happens, rather than causing errors by eroding an ensemble population that you're trying to sequence from, it simply stops. And then when the pause is over, it starts back up again. And it begins, and we've looked at this in some detail, it starts back up again with exactly the same level of speed and accuracy that it did before. Although, as I'm saying that, I'm reminded that there is an interesting thing. Another thing we learned about polymerases from being able to look at their activity in real time, at single molecule level, is that we found that polymerases have different gears. I mean, obviously, they're not built with gears. They have different intrinsic speeds. There will be durable periods of time at which it will sequence at one rate, and then periods where it will sequence at a different rate, and it has rare transitions between those. All of those are effects that come found on solid chemical systems, but at the single molecule level are untangled and allowed to be read without introduction of systematic error. The system is, the question was, how are you going to handle microbial sequences that are upwards of 75% GC content? We are in the process of trying to demonstrate, maybe working on a genome that will demonstrate this, but we're very confident that it will have no problem. The polymerase that we're using can work through those sequences without any difficulty at all. The sequencing that we've done, up to 85%, showed essentially no bias in the acquisition. So we're very comfortable that GC bias is going to be not a problem for smart sequencing.
There are some other microbial genomes that JGI has not been able to finish to structurally. You going to handle those?
Well, obviously structure is related to those pauses. Those pause sites that were alluded to before turn out to be, in many cases, reproducible in their genomic position. They are due to secondary structure, not in the sense, RNA is a secondary structure. We're sequencing directly from double-stranded DNA, so the secondary structure there is very subtle, related to the twist and ride that comes from the different bases and the way that they stack. But because it's double-stranded and because the secondary structure is very mild, we have not yet found, aside from those pausing signatures that affect all DNA sequencing systems, and ours would take less than most, we see no structural problems on the horizon. Yes?
Jonas at chunkdna.com. A very precise question and then a general question for both of you. Precise question. The 15-minute human genome will cost how much?
Well, it's going to cost the same as a fine dinner.
The general question is that I think in one stretch, we will be listening to the Edison of genomics, George Church, and then we listen to the Oppenheimer of genomics in a very focused way. Both gentlemen, of course, changed the world. Now, for the question for both of you, do you see this as a very clear path to a genome-based economy?
A genome-based economy? So, my imagination is spiraling out of control. I think that we are already seeing the beginnings of the genome-based economy. It is, I'm sure everybody is keenly aware of the economic downturn that we're in, and yet this sector of the economy is the one place that seems to be untouched by the downturn. And I think that's because of the incredible excitement that we're going into this. I know that there's still skepticism in the medical community about the value of genomics. I think that will pass. I think I'm preaching to the choir here. All of that, it's not going to amount to anything, but I think that this is going to be a $50 billion a year economy in 5 years.
We'll let George answer. Final question.
So often there are cases when there's a lot of places where there were two signals embedded in one of the copies. So it looks like a double basis on that.
So what that is, that's something that we look for very carefully. When in the very early stages of smart sequencing, we were concerned that some polymerases have an on-deck position, like in baseball, you use an on-deck circle where you stand. Some polymerases, including RNA polymerases, or even some DNA polymerases, have an on-deck circle for the next nucleotide, so that you could expect that there would be a second nucleotide bound. We looked at that very carefully because obviously that would either eliminate or greatly complicate the value of smart sequencing. What you're seeing there is not actually double residency, but rather channel crosstalk. Because the spectral emission widths of these fluorophores is broad, that there is some leakage in the different channels. So that when you see one of the channels going up, and if there's another apparent pulse underneath that, that's actually the same floor force leakage into the neighboring channel. Right, it happens in every single pulse, and we actually rely on it. We don't need to fix it. Because it's a predictable amount of leakage into the neighboring channel, when we don't see that, then we know that we're not looking at a